Is our final?
So the final is sometime after December 8th, I guess December 10th or December 14th or something like that. I don't know the exact time. It should be on your portal.
It says the 10th. Yeah, it says the 10th from 3 to 5.
That's it then, December 10th from 3 to 5. Okay. Oh, pumpkin pie is good.
Are we
Anyway,
gonna be doing like that proctor thing?
I don't know the details yet, but when I do know, I will let you know. For now, let's get started. This is now the second class in week 13, but we missed 2 days. So as I think I mentioned, it's the 24th class. And I'm going to start sharing. We are going to skip ahead a little bit because we're kind of running out of time and some chapters are just more important than others. We are going to skip ahead to chapter 19 on sampling methods and sampling distributions. So if you want to know if your soup has enough salt, you don't eat all of it. You only have to taste a spoonful, correct? If you have a small bowl and you want to see the taste, a spoon will give you the taste. If it's a huge pot and you want to taste, a spoon will give you the taste. Why is it that the same size spoon will work in both cases? Okay, this is the basics of statistical analysis, that you don't need a bigger sample size when you have a bigger population. It does not work that way. Okay, so methods of statistical inference. This is why we do statistics in the first place. Methods of statistical inferences allow you to make conclusions about the entire population based only on a sample. So for example, I'm sure you've seen polls, especially in the last few months, political polls about this one's going to win, that one's going to win. This one has this percent of the vote, this one has that percent of the votes. Have any of you personally been asked in any of those polls who you were going to vote for? I know I haven't. David, you were, really? Okay, well, that kind of defeats my purpose of what I was going with. But the point is that probably most of you have not. I have not, and yet somehow they make these predictions about, who's going to win. How can they do that? So the answer is the sample that they take enables them to make a prediction about the entire population. So if you want to use 1,000 likely voters to tell you about all likely voters, you've got to be very careful how you choose those 1,000 likely voters. For example, suppose I was interested in people's favorite sport. Suppose I want to know people's favorite sport. So I decide that I'm going to go to a Lakers game and I'm going to ask the people at the Lakers game what their favorite sport is. Does that seem like a reasonable way of determining people's favorite sports in general? No, why not? Or we can't hear you. Unless you're doing your Marcel impersonation, I'm not hearing what you're saying.
They already have a bias because they're at a basketball game.
That's right. There's a bias because they're at a basketball game. So chances are they like basketball in the first place. So how you take a sample is critical to being able to predict about the population from your sample. So the key idea of picking a sample is to randomize. You have to let chance choose the sample. You don't choose the sample yourself. You have to let chance choose the sample. So what are some different ways we can do that? Well, we'll get to it. There's many different ways of creating a sample. But before we get there, let's talk about our different definitional terms that we're going to use for this chapter. So one is the population. This is the set of people or the objects that you want to know about. This is everyone. Then you have the units or the cases. Those are the individuals, right? A case study. The population size is, of course, how big the population is. A parameter. This is a big one. A parameter is a numerical summary of the population, not the sample. It's a numerical summary of the population. What are some examples of numerical summaries of a population? What are some examples?
What are examples of what again? Sorry.
What are some examples of parameters of numerical summaries of populations? What are some examples of parameters?
Sample, unit of case?
No, I'm talking about a parameter is a numerical summary of a population. So what are some things that we've already done this semester that would constitute, there he is, that would constitute numerical summaries of a population?
Like age group?
No, I'm talking, I'll give you one, like the population mean. The
Oh,
population average is a numerical summary of the population. What's another one?
A percentage?
A percentage of what?
A percentage of gender?
Not exactly, but if I knew the percentage for the entire population, that would be a parameter. Anything that I know about the entire population is a parameter. Okay? Do I know, thank you, do I know the average height of every American?
No.
No.
No, but whatever that number is, that's a parameter, because that's a numerical summary of the entire population. Do I know the standard deviation for the entire population? Do I know the standard deviation for the entire population?
No.
I do not, but whatever it is, that's a parameter. Now, you don't know parameters. What we do is we try to estimate them. We try to figure out what they are based upon our sample. A census is when you collect data on the entire population. The entire population. How often does the United States perform a census? Anyone know?
Every 10 years.
Every
10 years?
Every 10 years. And they do, to the best of their abilities, they actually check and find out information on every single person in America. In fact, it is a federal crime to lie on a census, because they use the information to make federal policies and whatnot. And, you know, that's important stuff. The sample is, if you're not taking the entire population, but you just take a sample, then those are the ones that you're using to infer something about the entire population. So for example, if I want to know the average height of every American, maybe I'll take the average height of every person at CSUN. That will be my sample. Does that seem like it should give me a value that's close to the true value? Is there any reason why it would be biased? Do unusually tall or unusually short people tend to go to CSUN?
Yes.
Really? I mean, more so than anywhere else? More so than anywhere else? I don't think so. I think it would be fine.
Sorry, guys. Hold on.
It's okay. Liam is, the next generation. It's important to culture them and to bring them to math class so they can get an appreciation of math. I feel very strong.
Exactly.
Now, when you do a sample, it's going to have a sample size. The sample size is, of course, the number of units in the sample, right? So if I have a sample of, let's say, 1,000 people, that's a pretty large sample, I think. Even if it's estimating like the 300 plus million people in America, 1,000 is not too shabby. What is an estimate? An estimate is a numerical summary of the sample. It's a numerical estimate, a numerical summary of the sample. In a more advanced statistics class, that would be called a statistic. But in this class, we're just going to call it an estimate. So when I take the average height of every person at CSUN, and I use that information to find the average height of every American, that would be an estimate. Now, do I realistically expect that my estimates are going to be exactly the value that they're trying to estimate? If I take a sample of every one at CSUN and I use that to estimate the value for every American, do I expect it to be perfectly accurate?
No, because you're estimating.
Exactly. So there's always going to be a sample error. There's always going to be a little bit that I'm off. That sampling error is my estimate minus the true value.
I have a
Minus the
question.
parameter. Yeah, go ahead.
Can you round?
Well, you can do whatever you want. It's an estimate. No, it's only an estimate, right? If it's only an estimate, then do whatever you like. But the less you round, the more accurate it's going to be. So example, 20% of all Skittles are red. And I happen to get this random sample of Skittles where 3 of them are red. What is the population of this study?
Would you divide 3 by 20?
Not for finding the population. What is the population of the study?
20.
3 out of 20.
No, not numbers. The population is not a number. Population is a collection. What is the population?
M&Ms?
Skittles.
M&Ms.
Oh, Skittles. Sorry.
Wow, you're
Skittles.
just changing candy on me right now, huh? The population are all Skittles in existence. No, that was correct. That was not an X. Why? Who X'd me out? Okay, that should be done. Ding, ding. So that was correct. The population is all Skittles in existence. Now, what is a unit for this case?
One Skittle.
Skittles?
One Skittle.
One Skittle.
Thank you for repeating me. Now, what is the population size?
Is that how many total there
Yes.
are?
The population size.
13.
How much?
13.
13.
No. That's not the population size.
Oh,
That might be my-
20%.
That might be my sample size.
20% of all Skittles are red. You get this random
I
sample.
think you want to tell us the answer.
The answer is, who knows? It's how many Skittles are in existence? I can't answer that question. There's no way of knowing. It's kind of weird that they even asked that. How am I supposed to answer that question? The population size. How many Skittles are there? Well, I mean, I guess you can calculate how many Skittles are made every day and how many Skittles are eaten every day and how many days they've been making Skittles. And so, I mean, I don't know. That's a really weird question. The population size. It's nothing you can do there. But what is the value of the parameter that we're looking for?
20%.
20%. The proportion of red Skittles is 20%. They gave me that. Usually you will not be given the parameter. Usually you will not be given the parameter. Okay. What is the sample?
The 3 that are red.
The 3 that are red is not the sample. The sample is our handful of Skittles that we have. How many Skittles do we have?
13.
13, but that's not the size. That's a sample size. The sample is that picture. The sample are those 13 Skittles. Those 13 Skittles is our sample. We are using that to estimate the true value. So what is the sample size?
13.
13.
Oh,
That's the size of
Yeah.
our sample. Now, what is our estimate of the parameter? What is what is our estimate of the parameter? Based upon our sample, what would we think the proportion of red Skittles is? How would I calculate that? Guys?
3 divided by 13.
3 divided by 13. That's the percentage of red, excuse me. That is the percentage of red Skittles in my sample, 3 out of 13. Yes, no?
Yes.
What is that as a decimal?
23.
What is that as a decimal?
0.23.
How much? I'm sorry? I just didn't hear it.
0.23.
0.23. So now that we have that, what is the sampling error? Excuse me. Sorry. What is the sampling error? What's the formula on the previous page for the sampling error?
Estimate minus the perimeter,
Yeah. So what's the estimate?
20%.
I'm sorry. I can't. Maybe my sound is too low. Go ahead. Say that again.
20%?
Is that our estimate? 20%?
Oh, sorry. 0.23?
0.23. And what is the actual value?
Yeah, sorry. I
Well, they gave it to us.
20%? I don't know.
Well, the very first thing they say, 20% of all Skittles are red.
Okay.
Fact, right? They're giving me the parameter, 20%. Right? Yes? No? Maybe so?
Yes.
Yeah.
So our estimate is, I see some text here I missed. So their estimate is 23%. Oh, okay.
Minus the 20%, that would be 0.03.
Hold on. This is important. This is important. Sally, if they're really the best pumpkin pies, then I need her number and how to reach out to her. Thank you. But for the rest of us, what were we saying about math again? Because we should go back to math.
Aren't you on a diet?
Yeah, but not for pumpkin pie. That's a whole different thing. Okay, we got to be focused on what's important in life. Okay.
When you subtract it, you get 0.03.
When we subtract, we get 0.03. Okay.
Would that be the sample error?
That would be the sample error. That's correct.
Okay.
That would be the sample error. Okay. So let's fill out this one. Okay, a poll of 1,002 California registered voters selected at random from the list of all 17,717,936 registered voters found that 55% favored a legalization of marijuana. In the election, 57.1% voted to legalize marijuana. Describe these terms for this situation. So, what's the population?
17 million.
Voters?
Huh?
Voters?
Which voters?
The poll voters?
Say again, what?
The poll voters?
The poll voters.
The poll,
The
whoever.
random of the population. The population is 17,717,936, and they still managed to find me.
Yes, so the population, the population is the seventh, well, are the registered voters. The population are the registered voters. Okay, all of them. the third one, which is population size. What's population size?
$17 million.
17,717,936. That's the population size.
And the population is the same thing.
No, the population's not a number. The population of the actual objects, those are the registered voters.
Oh, registered voters.
Those are the registered voters. Okay, the population are the registered voters. Now, what are the units?
One voter.
Each voter is a registered unit, right? Each voter is a registered unit. Do we agree with that?
Yes.
What's the parameter here? What's the parameter?
Is it the number of registered voters?
No, that's the population size.
The poll of 1,002.
The parameter is a number. The parameter is a numerical summary of the population. It is a number.
Can you fill it out, Professor? I know you.
Well, I don't want to throw it out till you answer it. What is the
I know.
parameter?
55%.
It is 55%.
Between waiting for my printer, losing my internet, I'm like getting bits and pieces. I have to
Okay.
keep signing out, signing back in. It's so ridiculous.
I'm sorry, 17,717,936. This is the population size, and the parameter is 55%. I don't really understand census in this context. It doesn't mean anything, so we're just going to skip that. What's the sample?
1,000.
No, that's a number. That's a number. What's the sample itself? Not the sample size.
California registered voters?
No, the registered voters was the population.
Okay.
California registered voters.
That's the population. Okay.
Voters?
Which voters?
Legalized voters. Oh, wait.
No, guys.
The ones who favored to legalize marijuana.
No. The sample are the 1,002 who actually were in the poll.
Registered voters.
No, again, the registered voters are the people in California who are registered to vote. There's 17 plus million of them.
Okay,
Did I ask all of them for this poll? Did I ask all 17 plus million?
No, you only asked 1,002.
So those ones that I did ask, that's my sample.
Well, I was trying to tell you. I'm just kidding.
No, but what you gave me again was the sample size.
Just tease them. I knew wasn't there. Like again,
It's okay. Does that make sense? The distinction between the sample and the sample size?
No, can you?
The
Can you
sample,
out?
the sample are the actual people that I asked. The people. The sample is not a number. The sample are the people that were asked.
the unit or person. Oh, not the unit. Sorry.
The units. Yeah, the units, the people that I asked, that would be the sample. There's 1,002 in that sample.
So they should say sample of units.
Well, what do you mean?
Never mind.
Okay.
Just trying-
What's the estimate? What's the estimate?
57.1%.
57.1 what? Percent.
Voted to legalize marijuana.
57.1%. Huh? Sorry, David, what were you saying?
Oh, sorry, I was finishing up the sentence there.
Yeah, so say it again.
So it's 57% of the voters that voted to legalize marijuana.
Okay, so the parameter is that 55% favored it, but in my sample, 57.1% favored it. So what is my sampling error?
57.1 minus 55%.
So
57.1, which is
2.1%.
2.1%. Does that make sense?
So does that mean the 2.1% of people weren't accounted for? Like,
No. What it means is that any sample that you take or use, you're not asking everyone. So it's very rarely going to be the true value. It should hopefully be close to the true value, which is why we can then use it as an estimator. But I mean, listen, if I want the average height of every American and I use our class, am I going to get the true value? I doubt it. It'll be off by a few inches because it's just a sample. Samples are almost never exact.
So would this be a plus or minus 2.1%
It's
on either
positive.
side?
The estimate is bigger, so this is
Is
positive.
there- Okay.
This is positive. Okay.
So it doesn't matter if the sampling error is a percent or a decimal, it's just the
Yeah,
error.
it's the same thing. Same thing. Same thing. So we're gonna skip this class activity just because we're not in the class, although it looks really cool. I have no idea what that is, but that looks cool. Okay. So
Professor, I want to be sure, maybe it's me being dense. So
Probably.
for the sample, we always state what is being sampled, not the number.
the sample is the actual objects in the sample,
Objects, okay.
as opposed to the sample size, which is how many there are. Okay, it's two different things. Okay, so now random sampling. How do you actually go about and get a good sample? We know that if you go to a basketball game and you ask everyone, hey, what's your favorite sport? It's not a good random sample. So we want to see what is a good random sample. So selecting a sample at random from the population is a good method of sampling. However, it does not mean that every random sample will be representative of the population. For example, if I take 5 people from the class and as a sample for height, okay, let's see, I'm curious what the average height of every American is, and I could just pick 5 people from our room at random. If I happen to pick 5 people that are unusually tall or unusually short, then my value will be bigger or smaller than what I expect, correct? Okay, so not every random sample will be good, okay? But on the average, if I keep taking random samples of the same size, some are better than others, some are bigger, some are smaller, but on the average, it should again be a good estimate for the actual value. Does that make sense? Look at this little joke here. It's kind of funny. Over here, we have our random number generator, and it says 999999. Does that sound random? No, but if I ask you to pick a number from 1 to 10 6 times in a row, or I asked a computer to do it, is it possible to get 999999?
Yes.
Sure. So I don't know if it's really a bad sample or not, or not random. Doesn't look like it's random, but it might be. Randomness is tough. We've spoken about that before. Remember we had the chapter on runs? Remember that chapter on runs, that even something that's random is going to have streaks in it? Right, so you never really know. Okay. And in fact, we did introduce random sampling before. This is back in that chapter, I think. So here is the definition for random sampling. Okay, here is a definition for random sampling. Each group of n people has an equal chance of being in the sample. So let me ask you a question. Suppose you're standing in front of a classroom of 30 people, and you want to pick 5 people at random from that class. What would you do? Whether it's the good thing to do or not the good thing to do, what would you do if you were going to pick 5 people at random from a class of 30 people? Would it be correct to say, okay, you, and you? Would that be a good way of finding a random sample? Why not? Seems random. Like you didn't just go the first 5 over there. You went, you know, then you picked 5 people. Why is that not random?
Well, before it was because you'd have to, on a, like a line, it would have to steady out where there was no moving around or, up and down or whatever.
Yeah.
So it doesn't seem like it's enough people to get a random.
No. I just want to pick 5 people randomly from a room of 30 people. There's 30 people here, and I want to pick 5 people randomly. So I go you, and you. Why is that not random?
Because you're still pointing them out, or you're picking them.
So
yourself.
why is that not random? I'm asking why. I need deeper. Why is that not random?
Not random. You're choosing them.
I'm choosing them, but isn't any sample a choice at the end of the day? Isn't any sample eventually going to be a choice?
No, because you don't really know when it's like when you're just given a bunch of, like, say if you're choosing from a deck, you don't see the numbers, you're just picking the top 5 or whatever.
That's true. So what's the distinction between these?
One is like a blind choice in a way.
Okay. I love that. A blind choice. Okay, a blind choice is an excellent term to use. In fact, you've probably seen that term before in Grey's Anatomy and stuff, medical shows. A double blind study. You never heard the term double blind study?
Not ever.
You've never heard the term double blind study?
Never.
I'll just say I have so that we can move on.
Well, we'll get to a double blind study soon. The reason why this is a bad random sample is because if you pick 5 people randomly like this, one, you, and you, would you ever in a million years take the same 5 people in the first row? But if it was truly random, truly random, that would be a possibility. Every group of 5 people is as equally likely to be picked than the other group of 5 people. And if I pick you, and you, if I leave out the possibility of 5 people next to each other, that's not really a random sample. So what could I do practically if I really truly wanted a random sample? What could I practically do to get one if I had a room of 30 people and I wanted 5 of them? What can I really truly practically do to get a random sample?
You could number them all 1 through 30
Yes.
and match that to a random number generator.
Awesome. A name generator, a random number generator, awesome. You could even pick sticks with their name. You can have everyone put their name in a hat and shake the hat around and reach in and pick 5 out. If you did that, would any 5 people be as equally likely to be picked as any other 5?
Yes.
Yes. That makes it a random sample. That's exactly what makes it a random sample. So what are some ways we can do that? We could write each name on a card and then pick n of them. We can do what Angela suggested, number the units from 1 to n and use a random number generator to pick those numbers. These are different ways of getting a random sample. We can skip this. Okay. So far we've done 2 things. We had some introductory vocabulary concepts, and we had the introduction of a random sample. So now sampling distributions. And this is going to be very important as we go on to the next few chapters. When you take a random sample and compute a summary statistic, such as a mean, the summary statistic varies depending on which sample you got, right? If I take these 5 people and I average their height, I'll get 1 value. If I take these 5 people, in fact, I want to show you something here. So let me load up this following. Okay, and let me start sharing again. Okay. So what we have here is a is essentially a random number generator. What it does is it randomly picks a number from 0 to 100. Now, if I use the first case of the 8 cases, this graph suggests that every number from 0 to 100 is equally likely. If every number from 0 to 100 is equally likely, if I generate, let's say, like 30,000 numbers, how many of each should I get? Approximately. If every number is equally likely and I randomly generate numbers, how many of each should I get?
One of each?
You do 30,000, you're going to get one of each? If there's 100 numbers, if there's 100 numbers and I generate 30,000 randomly, and they're all equally likely,
300 of each?
so 3,000 of each.
Oh,
Or
sorry.
yeah, 300 of each.
Oh.
Well, no, you were right. But in general, the heights at the end should be roughly the same, correct? Let's see if it is. So I generated 29,703 random numbers from 1 to 100. And this is the shape I got. Does that seem relatively accurate?
Yes.
Yeah, that's one sample. If I do another sample, is that exactly the same as the first sample? But it's still pretty close, right? And if I do another one, these are all going to be different samples, but they're all going to be coming from the same underlying distribution. But they're all different. They're all different, but they all come from the same place. So every number is equally likely. This is how often I got each number. Seems pretty even for each one, correct? Yes?
Yes.
Okay. Now, since each one is different, there is some variability due to sampling or sampling variability. Okay, the samples themselves have some variability in them. But what if I take samples of a larger size? What if I don't take size 1, I take size, let's say 5, or better yet, even 2. I do 2 at a time and I average them. If I take 2 numbers at a time from 1 to 100 and I average them, do I expect many of them to be about 1 or about 100? If you take 2 numbers randomly from 1 to 100, do you expect their average to be about 1 or 100?
Yes.
How can the average of 2 numbers from 1 to 100 be 1? Only if both of the original numbers themselves were 1, correct? So let's see what it looks like. That's a very different shape. What does that tell us? We have lots of averages near the middle and not so many averages on the wings. The shape of the sampling distribution is different. In our example that we're doing here, when we take samples of more than 1 at a time, 2 at a time, 3 at a time, 4 or 5, and so on, the shape changes. Because when you take averages of samples, you get different values than if you do 1 at a time. So here's an actual example where we took samples 5 at a time and averaged them. What was the largest estimate in our sample? Look at that graph and tell me the dot plot. What was the largest estimate of our sample?
7.
Like 6.5-ish.
No. The largest estimate of our sample is the one. Remember, these are our means, correct? The dot plot tells us how many times we got each one. But which one was the largest? Which of those is the largest mean?
16.
16. How many times did we get a mean of 16?
1.
1.
So that's kind of like an anomaly. Which one, in fact, is the one that we got the most times?
The mean, or like the 7.
No, no, it's looking at the graph. Which one is the one that we got the most times?
Oh. I don't get the question.
Is that like 7?
6
I can't really see it.
6.87, around 7, correct? Right? 7 we got by far the most times, correct? Now, the actual population mean is 7.4. Was our value a pretty good approximation? It wasn't horrible, correct? 7.4 is only 0.4 off. So our sample average, or the one that we got the most times from our sample, is very, very, very close to the true value. So the largest estimate of the mean area from the random sample was 16. What was the smallest estimate, by the way?
1.5.
Yeah, about one. It looks like a 1.4, we'll say. It's a little under 1.4. The population mean was 7.4. What was the largest sampling error from any of the samples? What was the largest sampling error?
Would you do like 16 minus the 7.4 to?
That's exactly what sampling error is, right? It's our sample estimate minus the true value. They're telling us the true value is 7.4. Our largest estimate is 16. What's 16 minus 7.4?
8.6.
8.6. And about where is the sampling distribution centered? If you take a middle for this, where would it be approximately?
7.
About 7. Which is fairly close to the true value. Right? It's fairly close to the true value, correct? And that's not a coincidence. That is certainly not just not a coincidence. It's kind of like the point of this, all that we're doing. So I can't actually do this because, well, okay, here we go. No, we can't actually do this one. Okay, let's do this one. Despite knowing how dangerous it is, and despite the laws against it, 3/4 of drivers who own cell phones admit to texting while driving. That 75% admit to texting while driving. Do you think there are people who do it who will not admit to it? So probably the true value is much higher.
Yes.
Yes. Suppose you take a random sample of 50 drivers who own cell phones and ask them if they ever text while driving, and 42 say yes. What are N, which is the sample size, P, the true value of the proportion of the entire population, and P hat are approximate value? What is N? What is the size of our sample here?
50.
50. We asked 50 people. That is the size of our sample, 50. What is the true value of P? What is the true value of the population proportion, as far as we know at least?
0.75.
Excellent. The true value is 75%. They told us that. And we'll trust it because we have no reason not to. Of course, next chapter, we're going to learn about how to question things that we're told statistically and how we can do math to determine whether the approximations are correct. And what is P hat? What does our sample mean?
Say that again.
P hat is our sample proportion. Not mean, I said mean accidentally. P is the true proportion and P hat is the sample proportion. What is the sample proportion for this case?
Yeah, 42.
42 is not a proportion. 42 is a number.
Oh, okay.
And bigger than 1. Proportions have to be between 0 and 1.
0.84.
Where do you get that from? It's correct.
40.
But where do you get it from?
42 divided by 50.
42 divided by 50. Okay, makes sense? 42 divided by 50. 42 said yes. There's 50 who we asked. So 42 divided by 50. Okay? So part B, it says circle the sampling distribution for this situation. Which one of these is the correct sampling distribution for this situation? Well, where is our sampling distribution centered? Well, let me rephrase that. Sorry, let me try that again. Ignore what I just asked. If you're a note taker, cross it out. It made no sense. Let me start again. We expect that the sampling distribution should be centered at the true value of the parameter. The true value of the parameter is 0.75. Which of these is centered at 0.75?
The last one, I guess C, you can call it.
Well,
And,
C,
oh wait.
okay.
No, there's C and then there's A, which looks like 0.75 next to the 0.8.
It certainly does. What about the second one? Does that look like it's centered at 0.75?
Not even close.
Yeah, not even close. This one is definitely out.
Yeah.
Okay. Now, my sample had a value of 0.84. Can you imagine that if I took lots and lots and lots and lots of samples, I'd get lots of different answers? I get probably 0.82 and 41 out of 50 and 40 out of 50 and 39 out of 50 and 38 out of 50 and 37 out of 50. I get lots of possibilities, correct?
Yeah.
So which of the other two represents the fact that I'm going to get a lot of different possibilities, which center at 0.75, but give me lots of other possibilities? The first or the last?
The first.
First.
The first.
The first one, yeah.
Right, the first one. In fact, we go back up. Oh, someone texted something. Hold on, let me read that. More food. Sally, I'm not sure how long ago you said that. I just noticed it, but you will have to invite me for Thanksgiving. There's nothing else to it. It's settled. Okay, and invite your granddaughter with her pumpkin pie. So that's the only thing that's fair. Let's clear everything. Okay. Okay. So this graph shows the number of children per family in the United States. For example, about 20% of all families have one child. The average number of children per family is 4.1. This is just fact. Okay.
1.1.
Sorry?
You said it's 1.1.
1.1.
Yeah, you said it was 4.
I thought you said
yeah.
4.1.
My
he did.
apologies. My apologies. 1.1. Okay. So about 20% of all families have one child. The average number of children per family is 1.1. Okay. And if you look to the right, what you can kind of see in the right graph is the relative frequency. This is not a histogram. This is a bar graph. This is a relative frequency of all the possibilities for number of kids, right? How many families have 0 kids, according to this bar graph? How many families have 0 kids, according to this bar graph?
51%.
How about 51%, maybe 52%? Very good. How many have only 1 kid?
0.5. 0.1, wait. No, 0.05.
Something in the same ballpark, right? Okay, and so on, correct? Okay, now, these graphs show sampling distributions of the mean number of children for random families in the United States of size 4, 10, and 40. Of size 4, 10, and 40. Which do you think is which?
Families, these graphs for 10 and 40.
Which do you think is which? Think about that.
Oh, I think the third one, because 4 doesn't have any. Well, no, the first one does too, though. So 10.
Okay.
It's got to be 1 or 3, I think. Well,
there's 3 possibilities, right? 4, 10, and 40. Let me show you something here. Let's go up 1. Let's go up 1. Let's go up 1. Let's go up 1. Let's go up a bunch. 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 What's happening?
it's the same thing.
No, it's not the same thing.
Some might say it's getting skinnier like you.
It's getting... Angela. So yes.
That was a good one.
As the sample size increases, the shape might not change its overall shape, but it gets a lot skinnier because as you take larger and larger samples, you hone in on the correct value, and the things that you get from your random sample are much more likely to be close to the true value. Based upon that information, go ahead, please, and answer the question. Which of these 3 do you think comes from a sample size of 4, which from a sample size of 10, and which from a sample size of 40?
C, A, and B.
Which one is which? I'm sorry.
Oh, okay. C is the bar graph. That's 4.
No. Which of them is 4? Which of them is 10? Which of them is 40?
The middle one's 40.
The middle one's 40. The first one is 10, and the last one is 4.
And what tells you that?
The shape of the, I guess it's parabola.
Well,
And the solid black one means there's a lot of
Numbers.
numbers. Yeah.
Yeah, the one in the middle, all the sample averages are really close to each other. They're really close to each other, indicating a very high sample size. You don't have a lot of variation. The smaller the sample, the more the variation and the more spread out the data is going to be, as a general rule. So we expect the last one to be a sample size of 4. The first one, a sample size of 10, and this one to be a sample size of 40. Also notice, by the way, that the center is roughly in the same place in all cases, because we do expect them to be centered at the average. It's just the spread outness, the spread is bigger for smaller sample sizes. So as the sample size increases, the sampling distribution of the mean gets more blank in shape. The mean blank, while the variability blank. So let's go through that one. As the sample size increases, the sampling distribution of the mean gets more what? So let's go back to this one here. Let's look at a really weird one. Which of these 8 is the weirdest shape distribution in your opinion? Which of those is the weirdest?
The weirdest shape?
Yeah, we'll just pick one that's weird. Which of these 8 is the weirdest looking shape?
Let's go with 6.
Okay, let's go with 6. If I do one at a time with 6, I get something that looks like this. It's low for small numbers. It peaks, it drops, it goes back up, and it comes down again. So around 20 is very likely. Around 60 is somewhat likely. 40 a little less so. 80 a little less so. And 0 and 100 are very unlikely. When I take 2 at a time, 3 at a time, 4 at a time. As the sample size increases, already by 5, this is looking like what?
Pyramid.
But we have a word for a shape like this. This is looking very what?
Normal.
Normal. This is looking very normal. It looks like a bell curve. As the sample size increases, it looks normal in shape. The mean stays the same. While the variability does what?
Increases? No.
While the variability increases, it gets more variable. As the sample size increases, what happens to the spread?
Decreases.
It
It
also
decreases.
increases.
How does it increase, very Lori? The spread gets smaller.
But the spread, what do you mean by the spread again? Oh, you mean it's coming together?
How spread out it is. How spread out the data is.
Oh,
Right? As the sample size increases, what happens? The variability decreases.
decreases, silly.
Yes, silly. Write that down, please.
I did.
No, not you, everyone. Okay. Okay. So, oh, hey, and we're done. That was a small chapter. How nice was that?
It's a gift.
That was a pretty good chapter, right? It wasn't horrible.
That was amazing.
Oh, thank you, Angela. I really appreciate
Wow, I don't know if I'd say that.
Oh, I said that. By the way, guys, 29 pounds down today.
Congratulations.
Well, the first 30 is the easiest. You know what they say. So, after the first 30th, then
But hey,
change. But
it's in the
anyway,
right direction.
thanks. I'm going to stop recording.